In this problem, we're given a diverging lens with focal length -8 centimeters, and we have an object sitting 15 centimeters from that lens. We want to use a ray diagram with all three principal rays to find where the image is formed and approximate the magnification. And finally, we're going to use the thin lens equation and magnification equation to get the image distance and the magnification to 3 significant digits. Now on this grid, every 2 spaces counts for 5 centimeters, so you can see the object 6 spaces to the left of the lens. That's 15 centimeters. And this grid will allow us to make pretty good approximations of where the image is. So we start putting in principal rays. First, a ray coming in parallel to the principal axis will be refracted away from the near side focus. Second, a ray through the center of the diverging lens will be unrefracted. And third, a ray that comes into the lens aiming at the far side focus will be refracted parallel to the principal axis. Now on the right hand side of this lens, we see 3 rays that are diverging. And when you look through this lens, you're going to infer that there's an image producing this set of diverging rays at a point where they all have a common origin. So we're going to trace back all of these diverging rays to a common origin, and that's where the image of the head of the arrow will form. Well, 2 of these are already traced back. I just have to do the last one, and I always use a dashed line when the light ray is not actually there. We're just tracing its direction. And this looks good. All 3 of our rays are converging to a single common point, and I'm going to end up with an upright virtual image at that location. I can get my approximate image distance. It's a little bigger than 2 spaces, so a little bigger than 5 centimeters. I'm just going to call it 5.1, and that counts as negative because it's on the same side of the lens as the original object. To get my approximate magnification, well, my image is about 1 unit tall, and my original object was 3 units tall, so that's a magnification of about 1/3, and that's positive because my image is upright. Next, I'm going to apply the thin lens equation to get quantitative answers to these questions, and I'm going to solve for 1/di, the image distance, and my focal length was -8, so I have a -1/8 in there, and then minus 1/do, and do was 15 centimeters, so minus 1/15. So I can do this all at once in my calculator, -1/8 minus 1/15, and then 1 divided by that answer. I get -5.22 centimeters for the image distance, so that's pretty close to our approximation. Next we do the magnification, and that's given by -di/do. That's -5.22/15, and I get 0.348 for the magnification. So again, that's positive because our image is upright. It has not been inverted. And that 0.348 means the scale of the image is about 1/3 the scale of the original object. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.